Hi, my name is Luis Rivera, and this is my feedback detector project. According to the paper, one of the papers I've been reading, there's two different types of feedback. There's slow growth feedback, it's fast growth feedback. This project specifically is very good at dealing with fast growth feedback. It detects it almost immediately and eliminates it. Slow growth feedback, however, it takes a little bit longer to detect it, but once it has, it will eliminate it. So how does it detect feedback? The general idea behind it is it compares continuous FFT frames, checking to see if any FFT bin has consecutively increased by Y times its past value over Z consecutive FFT iterations. Y is set to equal 2.5, Z is set to equal 5. And these aren't random coefficients I found. These are coefficients that I read were good to use from a paper I've been using. If an FFT bin has met the prior requirements, feedback is taking place. So how do we remove feedback? So we keep track of that FFT bin that has met these requirements, and we take that bin index and convert it into frequency. So how do we do that? We take the bin number, so let's pretend like in this case it's 30, and you multiply by your sampling frequency, which might be 44,100, 48K, one of those, and you divide it by your number of FFT points. And in this project, I decided to use a 1024 point FFT. So 30 times 44,100 divided by 1024 gives you 1,292 hertz. So we'll be using that example. So let's pretend like the 30th bin was the resonant bin, and so yeah, that's the bin that the feedback detector said there's something going on there. So the next part is removal. So we apply a notch filter at 1,292 hertz. Again, we're using a 1024 FFT, meaning that because we're a zero, the 0th bin through the 512th bin is representative of DC through Nyquist. It means that one bin doesn't mean it isn't analogous to one frequency. It means you have 512 bins to represent around 22,000 different frequencies. So one bin is representative of not only one frequency. It's representative of a range of frequencies. And so if say the 30th bin is returned by the feedback detector, and you get 1,292 hertz, the feedback may be happening at 1,300 or 1,280. However, we did get close enough, and how would you increase this resolution? You would increase the resolution by taking a higher number of FFT points. However, if you do take a higher number of FFT points, it's more operations, and the feedback detection needs to be quick, so you get a higher resolution, but at what cost? So for now, this is good, considering that your notch filter isn't. The notch filter that you will be applying isn't only taking out one specific frequency. The Q, or the bandwidth, isn't small enough to be, or small or big enough to just take out one frequency. It's taking out a range of frequencies, which in this case, because of this 1024 number FFT points, it's fine. So how am I eliminating multiple frequencies simultaneously? This is something I didn't see in any of the papers, but I just thought I would try out, because why not? So I have a linked list of notch filter nodes that are only added to the list when feedback is detected. Samples are passed through this filter node list, and all feedback frequencies are eliminated. So say I have the feedback detector returns feedback at the 30th bin, and then after that it returns feedback at the 50th bin. So the way this works is that the linked list, it starts off with nothing, no filter nodes, because there is no feedback. It detects the first bin, so let's say the 30th, and applies the notch filter node to the linked list. And once it in its creation, it gets this number 30th, the 30th bin, and inside this filter node there's a biquad filter. And so with the number 30, it calculates the coefficients so that the biquad filter becomes a notch filter. And you feed it a Q and the frequency at which you want this notch filter, and at creation, and the notch filter node is made, added to the linked list, and then I guess 50th bin is detected. So same process, but the node is added after the 30th bin. And so what's happening? The samples are being passed through these filter engines through they're linked together, cascaded, really, and they after going through the first 30th bin notch filter, it goes through the 50th bin notch filter, and that's exactly how I'm eliminating multiple frequencies at the same time. So this project isn't 100% done, definitely not. It's 60 to 70%, I would say, done. There's still a lot of bugs and things I want to incorporate or keep testing and make better. And these are just some of the things I want to be working on in the near future, near goals, I guess. So I want to be able to calibrate the notch Q or bandwidth and gain appropriately for each instance of feedback. So if, say, the 30th bin and the 50th bin are detected by the feedback detector, and say the 30th bin needs more gain reduction than the 50th, I want to give that 30th bin the gain reduction it needs at one time, versus how I have it set now so that there's a default gain reduction of, I think, around 8 dB once there's feedback detected at a bin. So I want to do this this calibration Q and gain reduction calibration specifically for each individual case of feedback. So for now, each notch is initiated the same way, and that's something I want to change. That's something I want to automate. So next thing I want to automate is when the notch filter has been added and feedback is no longer detected, I want to automate the part where it takes out that notch filter that's no longer needed. So right now it adds the notch filter, but it doesn't take it out once feedback is no longer detected at that frequency. However, it might not need to be taken out. Maybe the gain reduction doesn't need to be as drastic. If, say, there's a 15 dB gain reduction at the at 1292, the 30th bin, and there's no longer feedback happening there, maybe I can bring up the gain reduction to -6 and see what happens. And if there's still no more feedback happening, then keep testing it and keep trying to go up maybe back to unity. Regardless, another thing I want to be looking at is implementing and comparing other feedback detection algorithms. The algorithm I'm using, it works, but it's not the best out there. But it never hurt anyone to look outside, and try to make make their things better. So that's what I want to do. However, so let's get things going. Let's test this. So let me set these controls. Normalize -100. All right. So first thing I'm gonna do is show you that I'm gonna be playing a wave file, a couple seconds of a wave file through this, and you'll see that the frequency response of the filter will remain the same, which is flat right now, because no feedback is happening. So the point of this is to show that on most occasions it doesn't detect. I mean, there are no false readings. So I'll be playing a couple seconds of this Welcome to Paradise cover. It might be lagging. I am in release mode. However, it might be lagging just because I'm recording. Yeah, and it usually doesn't, but yeah, just take me for my word. So let's get this going. The plugin is not bypassed.
Yo, turn the snare up in my headphones. Where's my snare? Shout out P-Mac. Shout out Maryland. Pretty cool team out here. Shout out Ross. Shout out Huey.
So, well, as you can see, there was no feedback in that wave file. So, I mean, there's nothing to detect, so there should be nothing to remove. Let's check the frequency response of the system. Flat. Yep. As I said, nothing to detect, nothing to remove. So let's try this again. However, I'm going to have sound input mode on. What does that mean? It's going to induce a feedback loop to occur on my laptop because I'm going to be using the laptop speaker and microphone. So I'm going to say a phrase and it's going to create a feedback loop here on my laptop. And I'm going to have the plugin bypass the first time through so you can see what frequencies are resonant here on the analyzer. And second time through, I'm going to unbypass it so you can see the feedback detector. Will detect that frequency or those frequencies and remove them. So let's have it a go. Bypass first. Sound input mode on. This is great. This is great. So, if you were paying attention, there was something between 1.5, 1.6K. There's definitely this right here. 2, 3, 4, 5, 6. Something between 5 and 6K, and also something up here. Something. Let's see what this is. Oh, can't really get to it, see what it is, but yeah, it's very high up there. So let's see if what happens when I unbypass this and say the exact same phrase. So let's unbypass it. Sound input mode on. I'll say the exact same phrase. This is great. This is great. So, as you can see, I said it. Not sure if something happened the first time I said it, but the second time I said it, there was definitely some cuts. The second time through, I think I said a little bit louder, and you see these cuts here, notch filters, and you might have heard those frequencies starting to build up, and perhaps before it even did to a point where we could even hear it, the feedback detector got to it and took it out. And as you could hear, there was once the filters were applied, it didn't sound great. I mean, yeah, this is a a really nasty looking frequency response. However, the feedback was eliminated. So I guess the next step in development here would be doing this. However, once the notch has removed the resonating frequency, the next step would be seeing how much can I put back, add to this gain reduction. So instead of having say minus 47 dB here, let me try and see if I can get away with minus 25 dB here, and see if there's the frequency is still not feeding back. And then keep going up until perhaps I get to unity and I'm fine again. However, as you can see, the feedback detection and elimination is working. However, the next step is in automating the filters themselves is not there yet. But let's give this a go again and let's see what happens. Actually, let me unload this. Load back in. Flat frequency response, there's nothing on the linked list. Alright, sound input mode on. It's not bypass. This is great. Yeah, you heard that. There was something going around 1 through 3K, and then at the end, you saw something here, right here. I'm not sure if this is 11K, but you heard it almost like beating, and then all of a sudden disappeared. Yeah, that was slow detection, slow growth detection, acting then again, a little bit slow. And let's see the frequency response. Yep, exactly. We saw something here, it was reduced. And then we saw something around here, it was reduced. Yeah, the notch filters were implemented, and at the end you did see that the feedback was no longer there. However, yeah, as I said, the next step would be trying to get these notch filters back up so that it doesn't have such a drastic impact as like this on our signal, because this is going to sound horrible. Say if someone's trying to give a speech or something, this is going to sound really bad. So if we can start bringing this back up to unity, and until we have a good balance between the and make sure that the feedback is still not happening, but we still have the close to somewhat of a acceptable frequency response, then we're golden, you know. So yeah, thanks for watching, and if you have any questions about my code, just email me, contact me, and I'd be more than happy to show you, run through it, and show you how my algorithm works and what I've done to make this happen. And so yeah, thank you very much.